Okay. You said it's a finite set of integer values who are 1, 42, and 13. Important to note is that this is basically, or not basically, it is just logically equivalent to 23 for 1, and it's also logically equivalent to 4, 1, 23. You're talking about these set of integers, those three are the exact same thing. You have strings of these integers, so 1, 4, 23, that is not the same as 4, 1, 23. Those are fundamentally different strings of elements. This is a finite set of character elements, same thing, with the values of G and O. It's not the same as the string of character values G and O, which represents a formal mathematical string of Go. Let me say that again. When you're talking about strings, a string of characters is functionally equivalent to an actual mathematical string. So a mathematical string of characters is equal to a mathematical string. So this can be written as either G and O, or it can be written as the string Go. This is not the case for sets because say you had a set of characters G and O. The reason that this is not functionally similar to a string GO is because if we were to have written a set like this, it is the same. These two things are the same. However, this does not really represent the string Go. And it would also be difficult because you can't contain duplicates. So anytime you would try to write a string, it would have to be with only characters that are unique, which puts a lot of limitations on words. Okay, and then the empty set is the empty set. Okay, membership. To get into club set, you basically say that X is in S. If with two F's just means if and only if. Shorthand because mathematicians are lazy. We say that X is in F if and only if X is an element of S. So we can say that 33 is in this set, G is in this set, 33 is not in this set, and 5 is not in the empty set because nothing is in the empty set. Usually the mathematical notation for this is that little, I forget what it is, epsilon, sigma, something. But you read that as is in. So X is in the set of values, which it contains only X. Okay, now we're going to talk about how you talk about two sets and their elements and how they play with each other. So a union of sets, S and T, if you have two sets, is all of the elements that are in both sets without the duplicates. So you can see here we have a set of values 1 and 2, and then another set of values 3 and 2. If you add or concatenate the two together, you would get 1, 2, 3, 2. However, since you cannot have duplicates, it ends up just being 1, 2, 3. This is like concatenating strings, except you just remove the duplicates. So anything concatenated with the empty set is just whatever that anything is. And then the empty set concatenated with the empty set is the empty set. Later on, there's still Venn diagrams, but the union is essentially you have two Venn diagrams and you have everything in both. I think get rid of everything. That's it. Both. So then I'll do that. Formal mathematical notation for this is just the U. So we would say like X union Y, you have two sets. The intersection is a set consisting of elements that are in both S and T. So that first one there, you have a set of elements 1 and 2, and then a set of elements 3 and 2. The only element that is contained within both of those sets is just the element 2. So the intersection is just that element 2. Anything intersected with the empty set is just going to be the empty set because nothing is contained within the empty set. If you want a Venn diagram example, it's just this little sliver in the middle here. And then if you have two sets which contain no overlapping elements, obviously there's going to be nothing in the resulting intersection of the set. Mathematical notation for this is this and symbol. So you could read it as X and Y, anything that is in X and also in Y. The difference of sets, S and T, is a set consisting of the elements in S that are not in T and is denoted by this backslash symbol. So in that first one, you can see that we have the set 1, 2, 3, and 4, and then we are differencing out 3 and 2, which leaves us with just 1 and 4. So you're taking everything on the left-hand side, and you're subtracting from it everything on the right-hand side. So if you remove if you remove nothing from a set, you will just get the original set. If you have 5 and 2, and then you take out 13 and 5, the only element contained within that second set, that's in the first set, is 5. Whereas it's 5, so you remove that, you're left with 2. And then if you try to remove anything from the empty set, you cannot do it. This is pronounced S without T. And then finally, if you're talking about two sets, you say that S is a subset of T if and only if every element of S is also in T. You have something that's known as a proper subset of T. Does not allow S to be equal to T because you could do things where essentially you just say, well, obviously, if you have set X and set Y, and they both contain the values 3 and 2, obviously X is going to be a subset of Y. That's not really that interesting. What's probably more interesting is perhaps if you have a second or third set in this case, 1, 2, 3, 4, called Z. And then we would say that X or Y is a proper subset of Z because it is not equal to Z. And then the mathematical notations for that are this one is a subset, so we say X is a subset, or X. Or the one without the line is a proper subset. So X is a subset of Y, but it's not equal to Y. And then you add the line if they are equal to each other. Okay. That's most of how you interact with sets. Questions on that so far? Cool. The size or cardinality of a set is just the number of elements in it. It's just the same as with a string. So if you have a set of 1, 5, -42, and 18, and you count them, you will be able to see that there's 4. And then the length or the size or the cardinality of the empty set is just 0. Now, relating entries of a string to sets, if you have the entries of a mathematical string, that will give you a set, which is just the values. So we talked about entries when we talked about mathematical strings. But you can see if you have a mathematical string and then you want to just talk about the entries of that mathematical string, it is just all of the values of which there are no duplicates. So the only unique entries contained within this mathematical string are 1 and 2. And here's some Venn diagrams. If you have S and T, there is S union T, although I don't think this one should be colored in. S intersection T is just the middle. S without T subtracts all the elements that are in T. S is a proper subset of T. And then I guess if you wanted to talk about just S being a subset of T, it would just be 2 concentric circles where S and T are overlapping because they have the same elements. Okay, questions on mathematical sets and how they differ potentially from mathematical strings. A lot of the time when you're working with Java sets, which we'll talk about next, you'll be using set notation or you'll be reading set notation in the contracts because usually we write contracts in mathematical notation. So it's important to know all about these things. Okay, question or no? Okay, I'm going to erase. Is that okay? Now we need to talk about Java sets. So similar to how we talked about Java queues, or in our data structure era of the course, sets are a data structure, just a way to store elements within Java's memory that is not just an integer, a primitive variable, a reference variable, an array. Sets are an OSU CSE component, meaning that they inherit from standard. They have a kernel interface, then they have a normal interface, and then they have actually 3 implementations. I think there's 3 different version sets, 1, 2, and 3, which is fun because usually there's only 2. So now we will be talking about Java sets. So set, unbolded in a different typeface, and also blue, very different than set, bolded, green typeface, different font, mathematical. Is a component family that allows you to manipulate finite sets of elements of any arbitrary type. When we talk about arbitrary type, what's my chalk? We're of course talking about the generic type T, which can take on many different forms. In this case, not the numbers, any reference types as well. Here is the picture, burned into your memory, hopefully, at this point. But we have another set 3. This is not going to provide any change to how it works. It's just another implementation class of the set. So set 1L, set 2, and set 3 implement all of the methods contained within set kernel, and standard. Standard, of course, has our classic clear, new instance, and transfer from. If it ain't broke, don't fix it. Set kernel actually has 5 methods as opposed to the traditional 3, which are add, remove any, contains, and size. And then the actual set class has contracts for 3 additional methods, which are add, remove, and is subset. You'll notice that there are 2 different versions of both the add and remove. We'll get into that later, but those are overloaded methods. So methods with the same name, but different number or type of argument. And we'll get into what those are. Okay, speaking of which, if you couldn't tell, a set is modeled by a finite set of T, where T's are the generic type. And this mathematical set is the one that we just talked about. See the previous slides if you are confused. Only one constructor, which creates an empty set. Whenever we're talking about sets, mathematically, we'll talk about this, or we'll draw it like this. Today, in terms of Java sets, I'll probably draw it the same way that I draw every other data structure, which is a reference, as sets are a reference type, and elements contained within the set are also reference types. However, because there's no order to the set, you really can draw sets however you want. So we have a set of natural numbers, 4, 5, 6. This picture right here, if we have a set that we call, let's say, S, could represent the set 6, 5, 4, could represent the set 5, 6, 4, could represent the set 4, 6, 5, so on and so forth, all the way down to all, 6 combinations of the set. Could represent any of those mathematical sets. No argument constructor ensures that this is equal to the empty mathematical set. Okay, example, the most boring tracing table probably in the world. Something to note, though, similar to how you had to define the type that you wanted to store within the queue, you have to do the same thing for sets. So here we're saying that we want to make a set. We wanted to store big integers, which again are that wrapper class that converts regular primitive integer values into reference types so that they can be stored in the OSU CSC data structures, because only reference types can be stored within these data structures. And then on the right side, the dynamic type, we say it is of type set1L. That is one of the 3 implementation classes that are provided to you. And afterwards, you will have a set there. Questions so far? Java sets. Okay. All of the methods for set are instance methods, so you call them on a set. So here is our set that we will be using for demonstration purposes today. Where S is initialized non-null variable of type set T for some T. Okay. First one, we have the add method. The add method takes in a generic type T to be provided at runtime. So in the contract, it will say that it is a generic type T, but when you actually work with it in Java, it will have to be an integer or a string or a natural number or something or the other. Adds X to this being the set. It creates an alias or a reference to X, so keep that in mind. It updates this because it adds the element to the set. And then if we wanted to talk about the contract, we would say that it requires that X is not in this. Why is this requires clause important? Exactly. We can't have duplicates in sets, so the requires clause here makes us certain that X is not in this. So when you're writing set code, a lot of times probably the most common error that I see is that people will just add a bunch of stuff to a set without first checking to make sure that what they're adding is not already in the set. And if you do that, you'll get an error. It'll say at requires clause violated, X is not in this. And then it ensures that the old value of this union with a set containing just the element X is the new value of this. Okay, so let's update our picture here. We have a set containing 49 and 3. 49. 3. And then we have a natural number which is just pointing towards K. Or I guess these are big integers. That's what we find as. These are big integers, not natural numbers. When we call SI add K, what we're doing is we're creating an alias to this variable 70. So afterwards, it's not shown on the tracing table, but 70 is aliased to both inside the set as well as the original value K, which you added to the set. Questions on add? Pretty straightforward. Note the aliasing here between the 70s, not shown in the tracing table, but visible if you draw a diagram of the situation, which is right there. You can see the alias. Okay, removes X from this and returns it, updates this, requires that X is in this, ensures that the new value of this is equal to the old value of this without the set containing just the element X, and remove what actually gets returned from the set is equal to X. So if we have our same set here, I think, we call si.remove K, where K is pointing towards just a value of 3. 70, A towards 3. And then we call si n equals si.remove K. That is pointing towards 17. What this is going to do is it's going to look through the set for the value of 3, remove it, and then alias it to the reference of n. So n will be pointing towards 3 instead. The main thing to note here is that you'll notice that K really didn't do anything. It was really only here to provide the object value, that which we want to return. So it is not required that what you are removing or that you have an alias for the value that you want to remove, if that makes any sense. Because the value of 3 was contained within the set, as well as the value of K that we were using to represent 3, the value that we wanted to remove from the set, were not the same. So instead of removing the actual alias, it just removes the object value contained within the set that is provided to it, which is an important note. And then afterwards, you can see we now have, oh, well, I guess I added it back, but let me remove it again. We now have 2 variables of type 3. We have the one that was removed as well as the original, which we used as a reference, not like Java reference, but like as a reference to remove from the set. So the precondition for remove X is in this is satisfied whether or not there is aliasing involving the 3s in this situation. The reason is because we do not use the reference value when we're talking about contracts. When we say X is in this, we are not saying that the reference value is contained within the set. We are saying that the object value 3 is contained within the set, which is important to know, which is cool because you do not need a reference to the actual value you're trying to remove, which gets very useful later on. Does that make sense? If it does not, speak now or forever hold your peace. Okay, remove any, removes and returns an arbitrary element from this, updates this, requires that there's actually an element in there, and then formal contract specification. So 3 is getting added back to the set now for this example. The big thing to note with remove any is that when they say remove any, they mean remove any. When you call it on a set, any element within that set is fair game in terms of which one is removed. So if you ran this program 3 different times, you could get that afterwards K is equal to 49. You could get afterwards that K is equal to 3. You also could get that K is equal to 70. Does that make sense? It's defined in the remove any, how it is called. In terms of the ones that you will use, I think it just returns the first element within the set, similar to how like Q works, but that's not always the intended behavior. So after calling si.remove any, could be equal to 49. Other possible outcomes are that it could be equal to 3, or it could be equal to 70. You don't really know. Okay, contains reports whether X is in this. So it's a Boolean value, which talks about contains. So if we have a set 49, 3, and 70, drawn up there, and then we have a natural number, sorry, big integer, lied to you, negative 58, and then we call si.contains k. Remember, we are talking about the object value, not the reference value. What will be returned by this function, or what will the Boolean be? False, because it's not contained within it. Where might this method be useful? Exactly. Since you have to make sure that something is not contained within a set before you add it, this is kind of a vital method to make sure that it's not contained within the set before you can add it. So this would return false. Obviously, if you changed k to be 70, and then you said ba si.contains k, this would return true. And the condition checked by contains is satisfied whether or not there is an aliasing involved, because of the same reason that the remove method did not need you to have aliasing either, because we're talking about the object values, not the reference values. Separate them out. Okay, size reports the size or the cardinality of this. Okay, so if we have a set of 3 elements and then we call si.size, what will be the value of n afterwards? 3. Thank you. 1, 2, 3. Okay. Questions on those? Those are all of like the basic set kernel methods. All right. Then, just as a reminder, overloading is a method with the same name as another method, but a different parameter profile, being called parameter profile, meaning different number, types, or order of formal parameters. A method may not be overloaded on the basis of its return type. So you cannot have a method foo, which takes in an integer, but returns a string, and then also a method called foo, which takes in an integer and returns a Boolean. That is illegal. Java uses the method signature, or the method or the parameter profile, I guess it's called here, to determine which implementation of the method body to use when it's called. So if you pass it 2 integers, it's going to use the version of foo that takes in 2 integers. If you pass in 2 natural numbers, it's going to call the version of foo which takes in 2 natural numbers. We bring this up because, similar to how there is an add method that takes in a generic type t, there's also an add method which takes in a set of t's, or a set of something called s, and adds to this all elements of s that are not already in this, also removing just those elements from s. So this is way easier to understand with an example. It updates both this and s, and it ensures that this is equal to the old value of this unioned with the old value of s, and s is equal to the old value of this intersectioned with the old value of s, which is very hard to visualize, very easy to visualize at an example. So we're going to get there. And so this add method is overloaded. The original one takes in just a singular value. The second one just takes in an entire set. So if you have a set S1, you basically add to it all of the elements in S2 that are not in S1. So in this case, the elements 5 and 6. And these values are also removed from S2, which is something that people forget a lot. So keep that in mind. So afterwards, S1 will be 1, 2, 3, 4, 5, 6. S2 should just be 3 and 4. The reason that 3 and 4 are not added is because you cannot have duplicates. This is nice if you have 2 sets because you don't have to worry about checking each of the elements. You can kind of just call the add method and it will do that for you. It's a lot easier than checking to make sure that every element within S2 is first not in S1 and then only adding it if it isn't in S1. In other words, it removes all of the elements of the old value of S2 into S1. It conserves objects of type T. So none of the values are actually lost. They're all still here. They're just in different sets. Okay, remove, same thing. Takes in a type, parameter type, and then also take in a set of t's. Same thing, removes from this all elements of S that are also in this, leaving S unchanged, so S remains the same. And it also returns a set of values that were removed. Same thing, it's overloaded. So what's going to happen? There's three sets that you need to worry about. There's S1, which is the original set, S2, which contains all the values that you want to remove from S1, and then S3, which will contain all of the values that were removed. And it'll only work on values that are contained within S1. So what happens is we say we want to remove all of the elements contained within S2 or contained within S1. Okay. We want to remove from S1 all of the elements that are contained within S2 and store them in S3. So the only values that are overlapping between S2 and S1 are 3 and 4. So those will get removed from S1. S2 will remain unchanged, and S3 will contain all of the values that were removed. So we have 1, 2, minus 3 and 4, which were removed and returned into S3. S2 remains unchanged. Add and remove. Good. Good on that. Okay. In other words, it conserves the elements of S1 and S2 because they wind up in this third set as opposed to being lost. Okay. Another important one is subset, which will report whether this is a subset of S. Doesn't matter if it's a proper subset or a regular subset. So if you have two sets that have equal amounts of elements and you call it a subset, it will return true. An example of this, if we have S1 dot is subset of S2, we're saying, are all of the elements within S1 contained within S2? Is that true or false? True. Now, the other way around, or if we have a different set, are all of the elements contained within S1, 3, 4, and 5 contained within S2? No, they are not. So this would return false. Okay, those are all of the methods on set. There's one more thing we are going to talk about though, and that is an iterator or iterables in general. Iterators are a way to loop over every element of a collection. So with queues and eventually stacks or arrays, iterating over elements is fundamentally easier to think about than it is with sets. However, iterating over all the values in a set is a lot more difficult to think about just because there is no order to sets. So the order in which you remove it is not predefined before the method is run, before you call remove. Sure, you can know all of the elements that are contained within the set and then call remove, providing a reference to those values, but that's difficult because how do you know what's in the set? Or you could call remove any, which is also a valid option, however, can return different things based on each time you run through the program. Iterators are another way to just iterate over a set. So here's a way you could do it with remove any. I'm actually going to draw a picture because I think it's easier to visualize here. But if we have a set, okay, what the set contains two values, 1 and 2. What we do here is we create a temp set. So this temp set is going to be, say, over here. It's going to be a new instance of S. Meaning that if S is of type set 1L, it'll be a dynamic type of 1L. If it is a type set 2, it will be of type set 2. And if S is of type set 3, it will be of type S3. Then we call temp.transfer from S, which what that does is essentially crosses the pointers. So now S is an empty set. And temp is everything that was contained within S. And now we say while temp.size is greater than 0, we call tx equals temp.remove any. So the first time that this happens, you might have that x is equal to 2. Then whatever we want to do with x, say that we are writing a method that wanted to count all of the even numbers in the set, we would call like x dot, well, I guess if this is a natural number, you do x dot divide by 10 modulo 2 multiply by 10, whatever. And then you count whether or not it is divisible by 2. So it is, so we increase our count to 1. That's our do something with x. And then we call s dot add with this variable here. So s dot add, 2 gets added back here. Next, we say, because temp dot size is still greater than 0, we call x to be equal to temp dot remove any. There's only one element in within x, so it becomes 1. This time, it's not divisible by 2, so we stay at 1 in terms of our count, and then we add it down. I guess this would point to there. So our set is exactly what it was before. The elements contained within it are 1 and 2. However, we've been able to perform some operation, count something about the elements within the set without having to worry about aliasing. This simply means that it will be the same type as S. Why transfer from rather than copy from? There's no need for a copy, and transfer from is far more efficient. And then also, we still want S to be empty at the start of the iteration. And this does it by transferring the references. Okay, so this code has the following properties. It introduces no dangerous aliases because at each iteration of the loop, whatever would be aliased to the old value, let's say that there was another value of 3, whatever would be aliased to the old value, so in this case 1, just gets reset equal to the new value. So this becomes 3, and then we don't have to worry about the fact that I guess it's 1. We don't have to worry about the fact that this used to be pointing towards here, this value of 1, because now it's pointing towards the new value. So we're changing references before it can introduce anything dangerous. If what you want to do to each element is to change it, then this approach works because you may change the value of x each time you run through the loop body, and it won't introduce any dangerous aliasing because of what we just talked about. And it's reasonably efficient, though it does use remove any and add, and these could be slow if you have sets of billions of elements, but that's usually not the case. It does introduce an alias, that variable x, when you add it to the set, but it's not a problem because immediately after you call remove any and you reset x to a new value. So it's not that big of a deal. Another way that you could do it is using a iterator, which is a way to iterate over all of the elements contained within a Java or OSU CSE data structure that implements the iterator class. And set happens to be one of those classes. So similar to, or I guess, getting caught up on your inheritance or object-oriented principles slides that we went over a few weeks ago, because set kernel extends iterable and set extends set kernel, and all of the classes implement set. All of the classes, set 1L, set 2, and set 3, must implement this iterable class, which has one method called iterator, which returns an iterator over a set of elements of type T. The contract here simply says that this dot seen and this dot unseen, so all of the elements that we have seen and all the elements that we have not seen become this, and the cardinality, or the size of the this dot seen and this dot unseen sets, is equal to the cardinality of this. Iterator is yet another interface in the Java libraries, so this is a built-in thing into Java, not an OSU CSE specific thing. We will return to decipher the contract later, but how you use an iterator, there's actually a very easy way to do it, is what's known as a for each loop. So any collection that implements the iterator class is going to allow you to do this, which is loop through for T, where T is whatever stored within the set. So you could say natural number X in S. What this essentially reads as is for each natural number X that is contained within the set S, you want to do something with X. However, the caveat with iterators is that you cannot change the value of x throughout the code. So this is a natural number. You cannot call x.increment. The caveat with iterators is that it provides you an easy way to iterate over all of the elements in a set, or a string, or a dictionary. However, you're not allowed to modify any of the elements within those sets. So it's very useful if you want to test something about each of the elements in the set. Not very useful if you want to modify any of the values within a set. This declares x as a local variable of type t in the loop. However, x is alias to a different version of s. Here's an example where you have a set of strings called dictionary, which maybe just has a bunch of words in it. And you want to count the strings of length 5 in the dictionary. Here's how you would do that. You would say int count equals 0 for each string word in the set dictionary. If word.length equals 5, count plus plus. This is okay because you're not changing anything about any of the strings. You're not saying word equals word plus an exclamation point. That would be illegal. However, you can test things about each of the elements in the set. That is totally fine. So in which order? The kernel interface contains the contract for the iterator method as specialized for the type set t. The contract specifies the order in which the elements are seen. So if you are very interested in seeing how Java determines the order in which the elements of a set iterator are seen, you can look in the contract for the iterator. Okay, and then this is going over the mathematical contract that I talked about, where a string of t called this.seen contains in order those values already seen in the for each loop up until this point, and this.unseen contains in order the values not yet seen in the for each loop iterations up to that point. The reason that they're strings is so that you can have a clearly defined contract. Because there is a defined order in which you loop over the elements, you can use strings as opposed to sets. So the concatenation of the string of t values already seen and the values not seen, and the finite set of t of values already seen and not seen, is equal to the entire set of this. Okay. And then the size is important to make sure that you're not removing elements, or you're not modifying elements, or you're not changing elements. So it must be said that you are always adding the elements to this.seen after they have gone from this.unseen. Otherwise, you would break the idea of an iterator. So for each loop, as opposed to the remove any method, introduces aliases. So you should not call any methods on S. If what you want to do to each element is to change it, the approach does not work because the loop body should not change X. And it may be more efficient than using remove any. So it could be faster than using remove any. So if what you need to do is not modify each element contained within the set, then the iterator is probably your best bet. If you need to modify each element within the set, then a for each loop, or sorry, a remove any type method is probably the better option. Okay, any questions on sets? Going once, going twice. I will put the attendance code back up then, and you guys are free to go.